Assalamualaikum warahmatullahi taala wabarakatuh. Good day everyone. My name is Ilham bin Abdullah. My matrix number DF250004. Today I will present our project on the static analysis of a ground supported water tank.
Assalamualaikum and salam sejahtera. My name is Haris Salihin Merazli. Matrix number GF250072.
Name is Dinesh, son of Shanmugasegar. The matric number is 250038.
Hi and Assalamualaikum. My name is Muhammad Syahrudin Jamie. My matrix number is DF250075.
This project focuses on the static analysis of a ground supported water tank. Water tank play an important role in storing and supplying water safely. The analysis is divided into two stages. First, identify the load and creating a free body diagram, and second, calculating water pressure, resultant force, centroid location, and moment of inertia. The objective is to ensure the tank is stable and safe under static condition.
Now I'm going to talk about whole structure analysis. Description of the water tank structure. 1.0 type of tank selected. Ground. Option A. Ground supported water tank was chosen. For this project, the ground supported tank transfers its weight directly to a reinforced concrete base at ground level. In contrast to elevate tanks that need columns or other supporting structures. For foundation design and static load analysis, this kind of tank offers a more straightforward and reliable structural structure. Besides that, function of the tank. The ground-supported tank's principal purpose is to store huge amounts of treated water for a consistent and dependable supply. It also balances water demand during periods of high usage and acts as an emergency reserve for things like maintenance, shutdowns, and firefighting. Now I'm going to talk about the typical location of the tank. Firstly, ground-supported water tanks are typically located on flat, stable ground near areas with high water demand, such as residential, college, and administrative buildings. Their placement depends on soil's ability to support the tank load. Not only that, water is distributed using booster pumps, or by locating the tank or higher grounds. Ground level insulation also allows easy access for inspection and maintenance. This is a clear view of the tank we chose near our university. Now I'm going to talk about the principal structure elements of our tank. There are 4 types, which is tank wall, foundation pad, slab roof, and supporting system. For the tank wall, it's a cylindrical concrete shell. The measurement is 0.2 meter thick reinforced concrete well that can withstand the lateral pressure of the water that has been stored in the tank. Secondly, foundation pad or base slab. The slab of the reinforced concrete that equally distributes a load to the ground while supporting the tank. Third, I'm going to talk about the slab roof, a concrete cap that adds a continuous loads to the tank walls while safeguarding the stored water. And lastly, supporting the system, soil structure interaction. The soil physically supports the tank, providing the reaction force required to withstand all applied loads. I'm going to talk about the identification of loads acting on the water tank. Firstly, the tank structure's self-weight, dead load. The self-weight is a constant weight of the tank's constituent parts such as the base slab, roof slab, and tank wall. Secondly, water storage with live load. The foundation slab experiences a vertical downward force due to the stored water acting as a live load. The water level in the tank determines the load. Thirdly, hydrostatic pressure or lateral water pressure on the wall. The lateral pressure that stored water applies to the tank walls increase with depth and peaks near the base. Finally, ground soil reaction support reactions. The tank is supported and the total weight of the structure and the water is contained is balanced by the upward reaction force produced by the soil beneath it. Now I'm going to talk about the free body diagram of our project, which I stated in the slide. And there is weight of the tank plus water, which marked in the diagram, which is typed at load and directions. And water pressure on wall, as stated in the slide. Now I'm going to talk about the assumed data. We assumed ground supported water tank, which is the parameter, the symbol and the value, internal diameter, which is 8 meter. Secondly, the internal diameter, which is 4 meters. Internal radius is 4 meter. For the water depth, height is 3.5 meter. Wall thickness 0.2 meter. Roof slab thickness 0.15 meter. Base slab thickness 0.4 meter. Roof diameter 8.4 meter. Unit weight of water 9.81 kilonewton per meter cube. And finally, the concrete unit weight is 24 kilonewton per meter cube.
So we move to the 4.0 part, which is lateral water pressure on the wall or resultant force to water press. In this part, the most important thing is to remember from this section is the pressure on the tank wall form a triangle because hydrostatic pressure. Hydrostatic pressure grows linearly with depth. So our engineering design is directly influenced by this distribution, which means the wall is value 0.2 meter. Must be structurally capable of handling the highest lateral force at the top and the bottom, where the biggest pressure occur. Any fluid storage system, security and stability depends on our capacity to control this behavior. Next, we move to the free body diagram of the tank wall. This is our free body diagram of this project. So, this free body diagram separates the tank structure to examine all the external forces necessary for maintaining structural balance. The system experiences vertical strain from the cumulative self-weight of the roof and wall. In addition to the real weight of the water contained, the downward pressure immediately posed by the vertical support response from the earth accepting and upward pull at the base. The internal water pressure produces a constant upward lateral strain on the inside surfaces of the tank walls. Ultimately, the whole system must achieve equilibrium, while the wall must be physically designed to withstand the external fluid pressure.
So moving on to section 6, the equilibrium analysis of the wall. First, we calculate the lateral water pressure, which give us a maximum pressure of 34.34 kilonewton per square meter at the bottom. Second, this pressure creates a total resultant lateral force of 60.09 kilonewton per meter pushing against the wall. Finally, the location of this force exactly on 1.167 meter above the base. These values are essential to make sure our world remains stable and safe. So next we continue with section 6, the equilibrium analysis of the world. Focus on the force at the base. First, we determine the best reaction force to keep the wall in equilibrium. The horizontal reaction force R sub H must equal the pushing force, giving us 60.09 kilonewton per meter. Second, we calculate the moment of the base at the base by multiplying the force with its distance. We get a total bending moment of 70.10 kilonewton per meter. This calculation ensures that the foundation is strong enough to resist the lateral pressure. Next, we move on the section 7, the centroid of the wall section. First, looking at the cross section of the tank wall, we have a rectangular section with thickness of 0.20 meter and a height of 3.50 meter. Second, to find geometric centroid, we calculate the coordinate. The horizontal coordinate x bar is 0.10 meter, which is half of the thickness. Finally, the vertical coordinate y bar is 1.75 meter, which is half of the total height. This gives us the exact center of the point wall structure mass. Next, why is the centroid important for structural behavior? There are 4 simple reasons. First, as the weight center, it ensures the wall's total weight transfers safely to the foundation. Second, for the stress calculation, it defines the natural axis needed to find bending and stress. Third, for wall stability, it helps us check if the wall will overturn or slide due to water pressure. Finally, for the bending resistance, it is the reference point to find the moment of inertia which keep the wall from deflecting. In short, the centroid have us guarantee the wall stay safe and stable.
Assalamualaikum and salam sejahtera. My name is Haris Salihin Merazli. Matrix number is DF250072. So for the moment of inertia of the wall section, so the formula is I equals to BH power of 3 over 12. So the value I represent the geometric resistance of the tank wall to bending caused by the lateral water pressure. And then the bigger the value of I, the higher the wall's ability to withstand bending forces without experiencing excessive deformation. So after calculation have been done, we found out that our I is 0.7146 meter power of 4. Okay, so for the discussion, the first one is effect of lateral water pressure on the wall. The water pressure acting on the tank wall increases linearly with depth. The pressure is zero at the top surface and reaches its maximum value at the base of the tank. This lateral pressure generates a resultant force that acts at a specific location, creating a tendency for the wall to bend outward, which subsequently induces a moment at the base of the tank. And then the second point is for the role of centroid and moment of inertia in structural behavior. Okay, so the cross-sectional geometry must be analyzed through its centroid and area moment of inertia. The centroid serves as the geometric balance point of the cross-section, which is vital for locating the axis about which internal bending stresses develop and understanding the alignment of the wall's safe weight. So concurrently, the calculated area moment of inertia is 0.7146 meter power of 4, quantifies the geometric resistance of the vertical wall section against lateral deflection and bending. A higher moment of inertia directly implies a stiffer wall structure that can successfully minimize structural deformation under hydrostatic loading, proving that the structural behavior is heavily influenced by cross-sectional dimension. And then the third point is key analytical finding. This analysis demonstrates that structural ability is heavily governed by a geometric configuration, as the relationship between wall thickness and height directly influences the moment of inertia and the resulting structural response to load. Ultimately, these findings underscore the necessity of basic static analysis as a prerequisite to any structural design, ensuring a comprehensive understanding of force distribution and elemental response under static conditions before any further engineering procedures are allowed.
So now we go to the conclusion. Our analysis showed that water pressure increased with depth, starting at 0 kilopascal at the top and reaching a maximum of 34.34 kilopascal at the 3.5 meter base of the tank. This creates a total lateral force at 60.09 kilonewton per meter that push the wall outward and generate a bending moment at the bottom. To safely handle this load, the circular concrete tank is designed with an internal diameter of 6.0 meter and a wall thickness of 0.2 meter, which places the geometric centroid of the wall coordinate 0.10 meter and 1.7 meter. So finally, this proof that proper concrete thickness and steel reinforcement are essential, making this basic static analysis a mandatory first step before any construction begins.